I'm the Reverend Johnny Healy. I'm RevNull on Twitter if you want to send me feedback, or revnull@gmail.com if you want to send me more than 140 characters of feedback. So I'm just going to start this by saying, don't panic. Yes, this is an extreme talk, and yes, it is full of code samples that are meant to be confusing and bewildering and frustrating, but this isn't really as much about writing ugly Python as you might anticipate. This is really more about pushing the extremes of what Python can do, and then exploring various novel control flows and things like that that you can explore. And so if you really did just come here to see the ugliest Python, you're in the wrong place. So some people have asked me, just like to give you one heads up, I am an expert. I love obfuscated languages. Like, the uglier the language, the better. And I write Haskell, actually, in my free time, just because I think that's a fun language, but it's confusing as hell. And I'd also like to warn you, I wrote a lovely Python module that allows you to use Haskell-style currying. Never install it. It actually uses some of the tricks I'm discussing here today. So whatever you do not attempt to try anything that I'm about to show you at home. These code samples are frightening and dangerous, and really, you don't want to do these from the safety of your house. But if you do feel the need to write obfuscated code, make sure you have a really good reason for writing obfuscated code. Job security is a good one, and it's also good if you want to write, misleading, malicious code, although I'm not going to discuss that too much. But in my case, the reason I started learning to write obfuscated Python is I had a coworker who, he had kind of an unpleasant demeanor and body odor problems, and his name was Lur. He was from Omicron Persei 8. He actually had a tendency to eat the coworkers that I did like, but he couldn't eat me because he couldn't understand my code. And so Lur and I had to learn to work and live together without eating or killing each other. So yes, obfuscated code can save your life one day if you have such a horrible coworker. So now I'm going to get on to the meat of the presentation, because you guys are probably tired of hearing about me already. So first thing I'm going to talk about is the assignment operator. The assignment operator in Python is extremely powerful. You can assign almost anything. If you can't find a way to assign it, keep looking, because really, almost anything, and by that I mean you can't redefine none. None, for whatever reason, isn't a variable. It isn't even a constant. It's a keyword. It's one of the few things that you can't reassign, though. Yeah. But here are some fun things that you've probably never tried, or hopefully never tried, to reassign. You can change the object type into the string type. This is something that's kind of fun to do. You can redefine the tuple type as a function that returns a tuple. And my particular favorite, you can switch the values of true and false. I like sticking this in my code because it's a good way to teach people not to import star. After they do that a few times, they'll stop importing your code. But there's actually, there is a way, I'll leave it as an exercise to you, that if someone does switch true and false, you can figure it out and fix it. Although this also is even better than just switching it in your module. If you do this, this will switch true and false everywhere. And it's really fun if you do this in IPython, because it breaks in a particularly hilarious way. And here's another trick you can do. You just replace the object type with something that raises an exception when it's initialized. So if you stick this in your code and people, don't write initializers for their various objects, then it will break. And also, on functions, there's this fun thing called func code, which I'll discuss a bit more in detail later. But the func code actually contains the code that's executed for a function. So here, as you can see, I've written simple functions to add and subtract, and then I've switched the code around. So the add function actually subtracts. So comparisons. This is another fun topic. I'm going to shorten this a little bit because a lot of these sadly have been fixed in Python 3000. So in Python, you can compare arbitrary types to each other. As you can see, 10 is less than hello world, and object is greater than type, and true is greater than the string true. You can also do weird various comparisons with not a number and infinity. And as you can see, not a number is less than, or it's greater than and less than infinity somehow, I guess because it's not a number. You can also, as you expect, compare a class to itself. It's equal. But if you take an instance of something, compare it, you'll actually get different answers. This is a really good way to introduce non-determinism into your code. And the reason this works is because if you don't define a comparison operator, it'll actually just use the IDs of the objects. So depending on which has the higher or lower ID, you'll get different results. You can't compare complex numbers to each other, though, because that's mathematically invalid. You can compare them to other things, though. So I had mentioned the func code. And so here, I'm going to talk a bit about code objects. Code objects are not for the faint of heart. And these are, in fact, not my words. If you call help on the code object, the documentation says, not for the faint of heart. This is, in fact, the only useful thing it says in the documentation. The rest of it is fairly undocumented, but some of the things I'll mention. The code string is particularly interesting. That's it's a string that contains the Python bytecode that gets activated. Some of the other fun things you can play with are the constants, which any constant you use in your code gets shoved into a tuple in there. And variable names, those also get shoved into a tuple. You can actually create code objects with variable names that aren't valid Python variable names and confuse people like that. So how do you get a hold of the code class? Well, they actually don't make it very easy. The best way I've found is to call type on a func code object, and that returns the type. So this is what bytecode looks like. This is a really good place to start analyzing. As you can see, it makes a lot of sense what this does. No, it actually doesn't help. A better place to look is in the fifth circle of the Python standard library, where you'll find the dis module. Dis is the disassembler, and it allows you to take a piece of, take a code object and disassemble it into the bytecode and see what that bytecode does. So here we have something. It just loads the x variable twice and then does a multiply and returns the value. It's a simple, square. So let's say you want to modify the code string. Well, you can't actually modify it, but you can create a new one and create a new code object. This is how you would iterate through it. And there's this useful opcode. If you look in the opcode module, there's this thing called have argument. Everything that's greater than have argument is something that takes a 2-byte argument, and those 2 bytes are shoved into the bytecode. Everything else doesn't take an argument, just does whatever. And so it's also, I think, the most well-named opcode in any programming language, because it's a nice little Monty Python reference there. So what are some things you can do by editing bytecode? You can replace all references to variables with constants, just on a whim. Or you can switch around arithmetic operators. You can write some code and then run it through a function that changes all the pluses to minuses and minuses to pluses. And you can rewrite functions to exhibit Haskell-style currying. Here's another interesting thing, the constants. So let's say someone you know uses the system function and executes some code. Well, you can replace their code with an identical code object that just switches the constants around and do all sorts of malicious things. Yeah, people don't like it when you do that, but luckily it destroys any evidence of what it did. So now this is one of my favorite topics in how to write obfuscated code, decorators. These are the secret weapon of the obfuscated Python developer. So you've probably written decorators that are, functions, or maybe once in a while you write a class that takes a function and returns a new, callable class. But you can actually turn any arbitrary callable into a decorator as long as it only takes one argument. And this one, as you can see, I'm taking the list, and calling the instance method of append, which takes one argument, and I'm using that as a decorator. This then, of course, breaks the contract of decorators because it doesn't return a function, makes the function difficult to call, as you can see. But the nice thing about using instance methods as decorators is that you can embed state into your decorators, and that allows you to do all sorts of fun things like write functions entirely in decorators. And if you're wondering how to do that, you just have to create a Turing-complete language completely in decorators, and then you write your code in the decorators and stick a stub function at the bottom. And for this, I'm going to use one of my favorite obfuscated Turing-complete languages. Some of you may be familiar with it. I'm not going to say it out loud for the purpose of keeping this talk clean. I'll just refer to it as, the language which shall not be named. But how does it work? Well, it takes this theoretically infinite set of bytes and a pointer that points to one of them. And then it has 8 operators. This is the first operator. It shifts the pointer to the right. There's an operator that shifts the pointer to the left. There's one that increments the value at the pointer, one that decrements the value at the pointer, an operator to read from input into the location at the pointer, something to output, and then you have these last 2 operators, which are the looping construct. The way these work, when you encounter the beginning of a loop, if the value at the pointer is 0, it skips to the end of the loop. Otherwise, it runs through until it reaches the end of the loop, skips back to the beginning, and performs the check again. So what does this actually look like? Well, let's say you want to read a string and output it in reverse. This, I've heard, is a very common interview question. And so this is the solution to that question. It looks a bit complicated, but it's not too bad. It just reads a character, and then it starts looping and keeps reading characters until it reads 0, which is the end of the input. And then it takes a step back and then starts outputting the characters until it's run out of things to output. So how do we implement this as decorators? Well, we'll create a class. We'll call it the engine class, and I'm rounding the infinite series of bytes down to 1024, which seems like a close enough approximation. And I'll start the memory location at 0, or the pointer. So we have our left and right methods, and these, of course, are meant to be used as decorators, so they return a new function. And I'm having the input and output be passed as parameters to that function, just to keep things simple. It'll make sense when you see it all together. So we have the left, which just decrements the pointer, and the right, which increments the pointer. Plus and minus are also not too difficult to read. You're basically incrementing or decrementing the value that's currently being pointed at. And after it performs these operations, it, of course, calls the next function. Then you have read and write. So the read just reads until there's nothing left to read, and then it just reads the value 0. And the write just outputs the value to the output string and passes those along. Now, the looping construct is a bit more complicated. For this, I've basically created an exception type that it takes the next function that needs to be called, the input, and the output. So when you reach the end of a loop, it raises one of these exceptions and passes the next function that needs to be called and the input and the output. So at the beginning of the loop, it just starts looping, calling the current function, and then once it catches one of these exceptions, it calls the next function with the input and output. So let's put this all together, see how it works. So we'll start by instantiating the engine, and then we create our series of decorators. And for the purpose of keeping this as terse as possible, I've given them all one character names. And that also makes it easy to take our original, program that we've written in the language that shall not be named, and we just convert it to the names of our decorators. Then we rotate it and decorate it. And then we stick a stub function. Now you'll see the stub function no longer cares about the input, because the input should theoretically be empty at this point. And then the output is the reversed string. So this does work. This example is perfectly valid. The only problem with writing code like this... Oh, yeah, a side note. When I was putting together the slides for this, I discovered a bug in the code. And so if anyone can actually, or the first person who can find me and identify the bug in it, it's a pretty horrible bug. First person gets a free beer, so... So yeah, this is the one problem with writing code like this, which is that your stack will overflow and crash fairly quickly if you nest too many decorators. So sadly, this doesn't scale too well. But that does lead me to my final topic of this talk: how to implement tail call optimization in Python. Now, as we all know, this is a big debate within the Python community, since Python doesn't support tail call optimization. And I'm only going to do very simple tail recursion. But feel free to take these ideas and run with them and implement full tail call optimization. So I think we should take a moment to understand how recursion works. And if you go back to lambda calculus, it's actually kind of tricky to implement, recursive functions in lambda calculus, which is the origin of computer science. But luckily, there's a very smart mathematician who figured out how you could do this. His name was Haskell Curry. This is a photo of him. His parents named him after their favorite programming language and food. But he was a very smart guy and figured out how, using only lambdas, you could write recursive functions. I am, of course, talking about the Y Combinator, which, for those of you who speak lambda calculus, it looks like this, and for the rest of you, it looks like this. Although for authenticity, I've implemented it here purely in lambdas, because yo dog, I heard you like lambdas. And so, how does a Pi combinator actually work? Well, it's a function, and it takes a function, and it returns a function, so you use it as a decorator. And the way you use a Y Combinator is you give it a function that takes a parameter, and for this we're calling it recurse. So what recurse does, or what the Y Combinator actually returns, is another function where you've got an inner function here that gets passed into recurse. So this inner underscore factorial actually becomes recurse so that you can call it recursively. And this is through some mathematical sleight of hand that is probably way outside the scope of this talk, and I don't really fully understand it, so I'll just skip past that. But this will also cause your stack to collapse. And I stuck a funny cat photo in here because I figured, people are probably getting confused by this point. And this is nice and light. But there is hope that we can take this and, add tail call optimization. And the reason for that is because, so we'll rewrite it as a actual tail call optimized version or tail call version where, the recursive function is the last thing that gets returned. And the reason that we can optimize this is that we're not actually calling the function recursively, we're calling this other function that's getting passed. So all we have to do is inject something into the code that changes how this recurse function behaves, and we can hijack the recursion process and pop it off the stack and do all sorts of fun things. So here I've re-implemented the Y Combinator in something other than lambdas, hopefully to make it slightly more readable. There are some unusual things in this code. For instance, you'll notice the Y Combinator gets passed a function x, which is later used as a decorator, which is not something you generally see in code, but The thing worth noting is this underscore underscore y, that takes args and quargs. That's essentially going to be what gets passed to our, as our recursive function into the function that's being made recursive. So how are we going to do this? Well, let's create a new decorator and call it thunkify. So if you're not familiar with a thunk, it's just a function that takes no arguments, and when it's invoked, basically does something. And this is a cheap way to implement lazy evaluation. So here we've created a decorator called thunkify that you can use on a function and changes it so that instead of actually calling the function, it returns a thunk. And then here I've implemented a runner function. So what the runner does is it's another decorator. It replaces a function with something that calls the function, and as long as it keeps getting something that can be called, we're assuming that's a thunk, and we continue calling it. Once we get something that can't be called, we assume the function is done, and the recursion termination condition has been reached, and so we return that value. And let's stick this into our Y Combinator. So, as I said, the underscore underscore y, that ends up being what gets called recursively, so that'd be a good place to stick the thunk. So I stick thunkify in there so that what gets passed to recurse ends up returning a thunk of the recursive call of the function. And then I stick the runner near the outside of the Y Combinator, and so it sits there waiting for the thunk, catches it, and keeps calling it. And this essentially trampolines the whole process off of the stack and continues to run it in an iterative fashion. So does it work? Well, I tested on factorial 10, and I'm sure if you've run factorial 10, you recognize this is the correct answer. But factorial 10 isn't very impressive. That's something that you can do in Python without tail call optimization. So then I ran it on factorial of 10,000, and it spit a whole bunch of crap out. It's a really, really, really big number, and I'll be honest, I haven't taken the time to confirm that it's the correct number, but 10 worked, so I assume 10,000 is good. What matters is that it, didn't crash our stack. And so that is the end of my presentation, but if anyone has questions.
We've got time for questions, so anybody that's got them, go ahead and queue up to the mic.
So I didn't see anything about meta classes.
Oh, yeah. Yeah, sorry about that. I had some other examples, but couldn't find a good way to work them in, and maybe next year I can find a good meta class example. Does anyone else have any questions?
Did we get the slides?
Yeah, the slides should be up on the site at some point. Oh, also be sure to thank the session staff.
I have a question.
Oh, good.
Could you try, from my understanding, to do the presentation in reverse?
Oh, do the presentation in reverse?
Yes, if you just go back to the slides and no, slowly, and try to explain in reverse. Maybe I get more of it. It was great. It was simply great.
So is the bug in your BF DSL that you weren't changing the location pointer in your looping constructs?
Let's see. I thought I was. Or actually, in the looping constructs, it doesn't need to change the location. The location is referring to where the pointer is pointing to in memory. And so what happens is here, when it calls fn, when it's calling the next function, that's the program counter moving. The location is only changing where the pointer to the memory is, not the code.
All right, thank you.
Hi, another try at the bug. I don't actually think this is the bug, but I just wanted to confirm that you have this behavior. You're supposed to be storing bytes in the language that shall not be named, but you don't truncate your data down to that size.
That is actually a bug, but
Okay.
that's not the serious bug, the serious bug is actually on this screen.
Ah.
While they're thinking, it occurs to me, if you wrote a Turing-complete language to implement functions and decorators, have you tried to see what the efficiency impact would be of writing these functions in decorators? And seeing if that is possible.
I haven't.
If it's Turing-complete, it should be doable.
It should be doable.
If you do not get an exception, exe won't be set?
Yes, you have won a beer. Wait, what? So the true semantics of this language.
I told you when you do the presentation in reverse, I will get more.
Yeah, in the true semantics of the language, it should skip to the end of the loop if when it first encounters the loop, the value is 0. But here, it actually has to go through the loop once, otherwise it throws an error here. So, yeah. Are there any more questions, comments?
Okay, thank you all for coming, and let's give another hand to our speaker.
Thanks.